Assalamualaikum and hi everyone. After we covered the root locus technique topic, now we will go through root locus design topic. In this topic, there are 3 learning outcomes. The first one is how to use the root locus to design cascade compensators to improve the steady state error. The second one is to improve the transient response. And the third one is to improve both steady state error and transient response. Previously in root locus technique, we saw that the root locus graphically displayed both transient response and stability information. To obtain a desired system response, adjusting only gain is insufficient. Therefore, overall system response design must consider the performance of transient response and steady state error. The locus can be sketched quickly to get a general idea of the changes in transient response generated by changes in gain. Specific points on the locus also can be found accurately to give quantitative design information. In improving transient response, flexibility of desired transient response can be increased if we can design for transient responses that are not on the root locus. For example, we assume that the desired transient response defined by percent overshoot and settling time is represented by point B. With a small gain adjustment, can only obtain point A. Unfortunately, on the current root locus, at the specified percent overshoot, we only can obtain the settling time represented by point A after a simple gain adjustment. Thus, our goal is to speed up the response at A to that of B without affecting the percent of overshoot. This increase in speed cannot be accomplished by simple gain adjustment since point B does not lie on the root locus. This figure illustrates the improvement in the transient response we seek. The faster response from poles at B has the same percent overshoot as the slower response poles at A. One way to solve our problem is to replace the existing system with a system whose root locus intersect the desired design point B. Unfortunately, this replacement is expensive and counterproductive. Rather than change the existing system, we augment or compensate the system with additional poles and zeros, so that the compensated system has a root locus that goes through the desired pole location for some value of gain. One of the advantages of compensating system in this way is that additional poles and zeros can be added at the low power end of the system before the plant. Addition of compensating poles and zeros need not interfere with the power output requirements of the system or present additional load or design problems. The compensating poles and zeros can be generated with a passive network or active network. Compensators that are used pure integration for improving steady state error or pure differentiation for improving transient response are defined as ideal compensators. Ideal compensators must be implemented with active networks, which in the case of electric networks require the use of active amplifiers and possible additional power sources. An advantage of an ideal integral compensator is that steady state error is reduced to zero. Electromechanical ideal compensators such as tachometers are often used to improve transient response since they can be conveniently interfaced with the plant. Other design techniques that preclude the use of active devices for compensation can be adopted. These compensators, which can be implemented with passive elements such as resistors and capacitors, do not use pure integration and differentiation. and are not ideal compensators. We call it as non-ideal compensators, and they are lag, lead, and lag lead. Advantages of passive networks are that they are less expensive and do not require additional power sources for their operation. Their disadvantage is that the steady state error is not driven to zero in cases where ideal compensators yield zero error. So back to the design objective. If we want to improve steady state error, we can use a proportional integral compensator from ideal compensator or lag compensator from non-ideal compensator. Otherwise, if you want to improve tangent response, we can use proportional derivative from ideal compensator or lead compensator from non-ideal compensator. How if we want to improve both steady state error and transient response? We can combine the compensator from the same type. For example, to improve both, we can use PID, proportional integral and derivative compensator from ideal compensator, or we can combine lag lead compensator from non-ideal compensator.